Okay, thank you, Basil. Yes, okay, well, first a little remark. I've heard so many nice talks about physics here and all that, but I'm only a mathematician. So please excuse me if what I say about physics might seem a little bit naive from time to time, perhaps all the time. Okay, so the physics doesn't work. Oh, it does not turn on. Okay, thank you. Okay, let me briefly outline the plan of my talk. I will first begin by recalling the basics of Bohm's theory of quantum motion, well, also known as Bohmian mechanics. Then I will give an example of short-time trajectory, a very elementary one. A remark. I will not discuss, if only by lack of knowledge, any philosophical, ontological aspects at all. So whether you favor Bohmian mechanics or not, I'm just going to do mathematics. You see, that's a way of protecting myself against remarks and all that. Okay, I will thereafter discuss a rigorous short-time approximation to the two-point action function. I really insist on the word rigorous. We're going to see why. I mean, this seems to indicate that there are non-rigorous short-time approximations, and this is indeed the case. And then I will construct a rigorous short-time approximation to the propagator of Schrödinger's equation, the green function. And I will use the latter to prove that short-time Bohmian trajectories are classical Hamiltonian trajectories. I'm speaking here of phase space trajectories, not only configuration space trajectories. So I will show that for a very short time, the quantum potential does not work at all. Someone mentioned an invisible hand the other day. So roughly you can say that this invisible hand starts working only after a while and not immediately, as is the case with the ordinary potential. And finally, I will very shortly discuss the quantum Zeno or watchpot effect as a consequence of these constructs. Okay, a few references here. What I'm going to say is actually has just been published in Physlet A. It's a joint work with Basil Hiley, who has done the physics. I take the opportunity to thank Basil for having taught me everything I know, which is not very much, about Bohmian mechanics and the implicate order. Yes. Then, okay, concerning the quantum Zeno effect, here's an archive paper. It has been submitted also elsewhere. It's about the Zeno paradox for Bohmian trajectories, the unfolding of the metatron. What is the metatron? Well, I coined this word using metaplectic and electron. A metatron is a particle which is guided by the metaplectic group, you know, the unitary representation of the double cover of the symplectic group. But okay, I will not talk about these things here. Good. So quantum motion, okay, I think that everybody is familiar with that. You take Schrödinger's equation associated with a classical Hamiltonian. Okay, I assume that the potential V may depend on time. It does not make the arguments more complicated. I assume smoothness. I mean, I assume that the potential is very nice, so you can do asymptotic expansions and everything. Whether this is really realistic or not is another question. But I make this assumption in order to make the arguments a little bit simpler. Okay, so if you write the potential in polar, the wave function in polar form, insertion in the Schrödinger equations yields a continuity equation and a Hamilton-Jacobi equation. It is a Hamilton-Jacobi equation. It's not something which looks like a Hamilton-Jacobi equation. It's really a Hamilton-Jacobi equation for the Hamiltonian H plus cube psi, which is the quantum potential. Okay, so in the continuity equation, the velocity field is given by the gradients divided by the masses of the phase function. And in the Hamilton-Jacobi equation, cube psi, the additional potential is what is called the quantum potential, and it's given by this expression here. I think this is well known, it's quite standard. Well, the mathematical formalism, which is very simple, actually goes back to Madelung's hydrodynamic model. Good. Then, what is the quantum trajectory? Okay, the quantum trajectory, or the Bohmian trajectory, is the phase space trajectory corresponding to the Hamiltonian H psi, which is the classical Hamiltonian plus the quantum potential. There's a very complete study of the Hamiltonian formalism for the quantum trajectories in Holland's papers. He's written two excellent papers about that, and where he shows that the motion is indeed Hamiltonian, but with H psi and not H itself. Good. Okay, we have initial conditions. X psi 0 is the initial location of the particle, and the initial momentum is the gradient of the phase at time t equal to 0. Equivalently, and this is a very useful formula, you can write the equation of motion in this form here. Okay, there seems to be, or there is a problem with the nodes, that is the points where the function psi vanishes, but actually it has been shown that you have almost always global existence and uniqueness for the Bohmian dynamics. It was proved by Berndl and Shelley, Goldstein, and so on in a communication mathematical physics paper. So this is well known, so we should not bother about exceptional points where the trajectory does not exist. Good. Okay, now I give an elementary example. Suppose I take a Gaussian, normalized Gaussian, and here we have a wave vector or wave number kx here. So we have an initial velocity here. And I choose for the Hamiltonian the free particle Hamiltonian, no potential here at all. Well, then you can show that the solution of Schrödinger's equation is given by this formula here. You can do it in several ways. You can, well, the easiest way actually to solve Schrödinger's equation when it can be solved is to use the metaplectic representation. But that's another story. I will come shortly back to that in a moment here. And after a few calculations, you get this formula here for the configuration space trajectory. And you see here, if you let t go to 0, then up to error terms of order t squared, you get x psi t equal to x0 plus vg. Vg is the group velocity t. So you really have a classical motion here up to an error term, which goes very quickly to 0 for short times. The momentum can, of course, be calculated in the same way, and you get initial momentum times plus t squared term. So in this case, this example, very elementary one, clearly shows my claim, okay, that for short times you have a classical motion. Good. For the general case. Okay, so what I'm going to do here, I'm not going to take an initial Gaussian, but I'm going to take an initial source particle. That is, I make an idealized, somewhat idealized assumption that is at the point x0, I have a particle with dimension 0 here. This means that I have to solve Schrödinger's equation with this initial condition here. When t goes to 0, then I get the Dirac distribution centered at x0. In this case, the function psi is precisely the quantum propagator. The quantum propagator, or green function, is defined by this condition. It's the function g here, okay? And in this case, okay, if you want this function to be the solution to Schrödinger's equation with initial condition psi 0, you really have to have this condition here. So this function is really green functions. And I'm going to try to calculate approximations to the green function here, or propagator. Yeah. Good. One example. If you take the free particle, potential equal to 0, in one dimension, the propagator is given by this formula. It's well known and well physicists like to prove this as a consequence of Feynman's path formula. Actually, again, it's rather a mathematical consequence of the metaplectic representation, but okay. Well, then the function we have here in the exponent is called the generating function for the motion here. That is, it means that the equations P equal to the gradient of S and P0 equal to minus the gradient of S determine the motion here. This is trivial to check. S physically is the action needed to go from the initial point x0 to the final point x in time t with velocity p0 over m. A very important thing is that x and x0 are independent variables. They are not here related by any functional dependence. That is, when you write this here, sorry, let me go back here. I do not assume that x is a function of t. They are really independent. In the physical literature, S is also called Hamilton's two-point function. In the optical literature, it's called the aconal, and it has many other names. Action sometimes also, but the word action should be a little bit cautious. I'm going to show you why. Well, in the general case, that is, when you have a potential, when a potential is present, you try to find a green function by mimicking the free particle case. And you look for something, I'm too enthusiastic here about this, something like this here. Oh, yes, okay. Where S is the general generating function, which always exists, at least for small time. And the term rho is the Van Vleck determinant, or Van Vleck density of trajectories. This is very well known, actually, and one finds that this is not the exact quantum propagator. It's an approximation, but how good is this approximation? Let's see this a little bit here. Good. Yeah, so I try to look for short-time approximation. Good. So in the literature you find many, many different expressions, suggestions, and ansatz for the short-time approximation to the action function. These are usually called the midpoint rules. So, well, some others use this one, some others use this one, and some others use both. Okay, I'm not going to tell you which others do that, because, unfortunately, they are all incorrect. Well, so before you throw rotten tomatoes at me, let me give you an example. And then I'll tell you why, although they are incorrect, why they work for derivations of the Feynman integral. Don't forget that the x and x0 are independent variables. Good, let's take the harmonic oscillator, one dimension. Well, the classical Hamiltonian is this here. The exact formula for the action is this function. Well known. If you like the Feynman integral, you can use it to derive this. If you prefer, as I do, the metaplectic group, you make a calculation and you get this here. Okay, now let's approximate this for small times. Well, we use the school approximation sinus omega t almost equal to omega t and cosine omega t almost equal to 1. Using this, you get this nice formula here. So the first part is the free particle propagator. Well, what can I write this here? Of course, here. And then you get this term here, 6 here, and then this sum here. Now, if you use the midterm or the midpoint rules, I just wrote down here, you get respectively this and this. Not only do these two rules not agree with each other, but they do not agree at all with the correct formula. So, now, okay, let me tell you why these assumptions here work. They work because in the Feynman integral literature, when you make these approximations, you at the same time introduce a dependence of xj on the initial conditions. That is, xj is also a condition, is also a function of time. Then, if you do all the calculations, you really get approximations of order t. And then you can do your infinite products and all this. But to claim that these functions here are approximations for the generating functions is absurd, as I just showed here. Good. So what should we do then? Well, you make the following ansatz. That is, you write that the generating function is a free part plus an error term. And this gives, oh gosh, here. This gives this formula here. You see, the error term you have here is V tilde. And V tilde is just the average value of the potential between the points x0 and x taken at the initial time t equal to 0. If you apply this formula to the harmonic oscillator, you immediately get back the formula I wrote a moment ago here. So this was proved initially by Macri and Miller, two guys from Berkeley a long time ago, and I rediscovered without knowing this. Well, rediscover does not mean anything, but I proved this formula in a slightly different way, here. But Macri and Miller wrote a paper just telling, they are themselves physicists, telling physicists that one should be careful with the midpoint rules because they are false. Good. Once this is made, this will allow me now to write a short-time propagator. And this short-time propagator has this form here. That is, for the phase, I take the correct approximation to the generating function. And for the factor here, for the Van Vleck density, I just take the matrix of second derivatives, of mixed second derivatives of the action function, which is given by this function here. Notice one thing, that in this approximation, the rho tilde here does not depend on x at all, which makes the calculations much easier. Fine. So what happens now? Well, the main property of this approximate propagator is the following, that if we have the true solution of Schrödinger's equation here, and if I call psi tilde the approximate solution of Schrödinger's equation obtained by using my short-time propagator, well, the difference between both is small, of order t squared. So this is indeed a good approximation. By the way, using this approximation here, you can show that my initial assumption here also is a short-time approximation of the same order. But okay, we will not need this here. Fine. So I'm going to use these facts now to show that short-time Bohmian trajectories are classical. Okay, again, I use the equation here for the configuration space trajectories. I can rewrite this in more compact form here by introducing the mass matrix. Capital M is just a diagonal matrix whose entries and non-zero entries are the masses. Okay. Or if you prefer, you can think about the case n equal to 1. Good. Fine. If I now replace G by its, G being again the true propagator, if I replace it with its approximation G tilde, I got this here. And using this formula here, this approximation formula for the action function, what I get is these rather complicated things here. You see, now I have approximated the equation of motion with this equation here. What am I doing? I'm sorry for the mess here. Now we have a difficulty, actually, because the equation is singular at t equal to 0. Hence, this initial condition is not enough to allow us to solve it. So I have to use something else. But don't forget one thing. We also have to use a momentum. And in the case of a point source, represented by a Dirac distribution, the momentum, initial momentum vector can have any magnitude and any direction. So let's call it P0 simply here. And after a few calculations, here is what you get here. Okay, summarizing after these calculations here, the phase space motion is described by these two equations here. That is, x psi t is equal to the initial position x0 plus initial velocity t plus a term of order t squared, and the momentum is given by the initial momentum, which is totally arbitrarily chosen, minus the gradient of the potential at the point x0 at time t equal to 0 plus against an error term here. Yeah. Good. Now, these two equations here are exactly up to the term order of t squared, the solutions of the classical Hamilton equations. Just take the classical Hamilton equations for the Hamiltonian kinetic energy plus potential. Solve these equations up to order t squared. Then this is exactly what you are going to get. So this shows that asymptotically, up to error terms of t squared, the short time quantum motion is exactly the classical quantum motion. In fact, you can refine this a little bit and show that the quantum potential itself, it's very small for small times. It is, in fact, of order t squared itself, as opposed to the value of the normal, of the usual potential. Yeah, and this fact here, okay, I'm just going back here to the initial equations. You see, it's a little bit tricky. Well, it's elementary mathematics, but it's a little bit tricky to solve this here because you have first to find this equation here by approximating the true Green function. But then you have to differentiate this again with respect to time and multiply by m. And doing this, you get this equation here. And then you can actually do some calculations and get this formula here. This formula is the trickiest to obtain, but this formula also shows that the potential or the equation for the momentum is classical as well, because the configuration space, that the configuration space motion is classical, is already clear from this formula here, okay? The difficulty is 5 minutes, okay, let me be short then. Okay, so I said I would shortly discuss the quantum Zeno effect. As my mentor Basil Hiley pointed out, this result can provide a rigorous treatment of the watch pot effect. If we keep observing a particle, okay, a point-like particle, if unwatched, it would make a transition from one quantum state to another. We'll now no longer make the transition because it's classical. The unwatched transition occurs when the quantum potential grows to produce the transition. Continuously observing the particle does not allow the quantum potential to develop, so the transition does not take place. This was actually already in Holland's book many years ago, but it was just a very empirical argument he used, and then he gives a nice picture and all that. And actually, well, there was no proof. So what I have done is given a proof of this. So this result and a discussion of this will be published elsewhere soon. By the way, you can also show what I've been using. I've been using an initial wave function, which is a Dirac measure, so it's perhaps not so realistic. The calculations are a little bit more complicated if you take an arbitrary initial wave function, but everything works in the same way. Remember my example of the Gosson in the beginning here. So I think there are interesting things to do. And just I want to say, a last word. I give the last word to Pablo Echenique Roba, actually, who published a lovely paper in Archive, Shut Up and Let Me Think, or Why Should You Work on the Foundations of Quantum Mechanics as Much as You Please. This is a very good advice, and this is more or less what we are doing here, I think, here. So thank you for your kind attention.
Right, are there any questions now? We have 5 minutes. Yes.
The folklore about the path integral is that for...
Excuse me?
The folklore about path integral is that for small times,
yes,
you can use classical.
Yes.
And it doesn't matter which
exactly.
value of the potential you take.
Exactly.
Initial, final, medium. But as soon as you include a magnetic field, you have to take the midpoint rule. Do you agree on this?
Actually, I have to contradict you a little bit, because in my book, your 2000 book, I showed that you also can have approximate solutions when a potential, electromagnetic potential is present. But the formulas become very complicated. But again, you don't see it when you do Feynman integrals, because you introduce a time dependence between the variables. So the formulas work anyway if you use the midterm point rule. So but again, I mean, in the Feynman literature, well, it works, but for the wrong reasons. Well, I know you should not attack Feynman, but okay.
Helmut.
Yeah, no, it's only short. When you put numbers in your equations, let's say for
this I have not done.
System, yes.
This I have not done. So an interesting question is, I mean, the motion is classical on small time scales. Do these time scales coincide with what is called the Ehrenfest time, used in semi-classical mechanics? I don't know, and this is certainly something which deserves to be done. I mean, for how long is it really classical? So.
I wanted to make a very simple remark on the quantum Zeno effect.
Yes.
Because usually people, well, actually, I think we have discussed it with Fond and de Gasperi much before than other people have discussed it. But usually, it is one considers the limit for infinitely frequent measurement without taking into account that if you want to make infinitely frequent measurement, you have to shorten the time of measurement.
Yes.
And then if you take into account the indeterminacy principle between time and energy, you show that you have a shrinking of the region in which you have deviation from the exponential, and the game is not so simple.
No, that's right. There are several approaches to the quantum Zeno effect, but here actually you can take in this case you can take big frequencies of measurements. You don't even have to do it continuously, actually. No, it's true. Yeah, you can have a kind of stroboscopic effect. Yes, you're absolutely, yeah.